Number 71. What current is needed in the top wire in figure 22.5a letter A to produce a field of 0 at the point equidistant from the wires if the currents in the bottom two wires are both 10 amps into the page? All right, so please review number 69. All right, I'm piggybacking off of that problem, and here's where this stuff comes in. All right, so this now right here is what we have discussed from number 69. I'm going to work off of this because otherwise it's basically the same type of a problem. I just have to make two changes, okay? So if you notice in that problem, I called this I1, I2, and I3. And these were then the magnetic fields that were produced by each of them. Here are their directions and so on and so forth. So now what's going to happen in this problem is that they're saying make I2 and I3 both 10 amps. Now here's the thing. This is already 10 amps. We already calculated the magnetic field strength, right? They're both Tesla. Now I3 is not going to be 20 anymore. It's going to be 10. So guess what? This number is now going to be identical to beta B2, right? 3.46. They're no different. The directions, by the way, haven't changed also because they're both pointing into the page, so that also will stay the same. But now here's the thing. They're now changing the question. They're saying, well, what should happen to the current here in order for the magnetic field at the middle point, at that equidistant point here right in the middle, to be 0? Well, if you look at the free body diagram, basically, that we have, or something more or less, right, the vector diagram, whatever the heck you want to call it, there's no way that the way these forces are oriented at the moment, there will ever be a cancellation, right? Because there's going to be a net to the right somewhat force. The only way to do that is to take B1 here. Let me see if I can get that. Not sure if I can. No. Oh, there it is. The only way to do this is to take B1 and go like this. Point it now the other direction. Okay? It's got to be pointing in the other direction. You can kind of already see, right, from this picture that, okay, I kind of get it. There's no way it's going to cancel from the other direction. It's got to be pointing now to the opposite side. But here's the thing. You change the direction of this magnetic field, what the heck do you think is going to happen to the current? Well, it ain't coming out of the page anymore. It's now going into the page. So that's the first thing. Right? So the first thing is the direction now of that particular current has to be now into the page. Right? Now what we're going to do, and by the way, it is no longer this value because it might have to change. So why don't we now find out what that should be? So in essence, you know, we could do a whole table here with values and so on and so forth, but I think this is a lot easier. If you notice, if each of B3 and B2 have the same magnitudes, which they do, won't their Y components cancel? Right? Won't this component be identical? Right? This component of that vector B3 be identical to that component? I know it's not to scale here, but right? Well, that's because the problem before wasn't really, but actually that has nothing to do with it because B3 is technically should have been larger than B2. So I just, I'm not really taking this stuff into a scale into account. The videos are already long enough. So what I realize is that the Y values will totally cancel. So I only care about the X values then, and I know that they're both going to add up because whatever X value B3 has will be added to then whatever X value B2 has. So in other words, what I want to do is just find the X value of one of these. Okay, so to find the X value, right, we use cosine of 60 then, and then that's going to equal the X value, right, divided then by the hypotenuse, which is each of these B3 or B2. So now here it's the 3.46 times 10 to the minus fifth, right, cross multiply, so take your cosine of 60. Cosine of 60, I'm going to use the exact value from the calculator from before, since I'm just doing this, I just basically did the problem before. And then I get a value of about 1.73 times 10 to the minus fifth for one of them, but then you got to multiply it by 2 because you got two vectors there pointing to the right. So this now works out to, oh, wait a minute, oh my goodness, right? It works out to the same exact number. Interesting, right? So when you add those two together, the net x vector here is going to be the net x. So B, I'll call it 2, 3. In the x direction here would be 3.46 times 10 to the minus fifth, right? That's Tesla. Now that exact X force here, magnetic field here, B23X, has to exactly oppose B1. So I know now technically B1 here, B1 we'll call it, put this in blue, right? B1 here should now be negative, right? In terms of the sign, it just tells us the direction, but the magnitude is what we're going to need in a second. So it turns out to be exactly this value. Now how do I find its current? Well, that's why I'm going to use this formula, okay? I'm going to use the same formula I used in the prior problem. It says that the magnetic field produced by a particular current, in this case we're talking about current 1, will equal the permeability of free space multiplied by the current, I1, divided by then 2 pi times then our R value. What was the R value? Take a look at number 69, okay? So B1, this is going to be 3.46 times 10 to the minus 5th. This is going to be 4. Actually, you know what? Let me just solve this darn thing for I already. So just simply do some cross multiplication, boop, and boop. You see how fast all that math is, right? At this point in the physics class, you definitely want to be in that position. You don't want to spend too much time thinking about how to do the algebra. The problems are hard enough. So this is then 2 pi times that radius value. And what do we have from the prior question? We had, it was like 0.057 something. Let me go back and find it. Hello? Wow, we did a lot of work. Okay, yeah, this was 0.0577. All right. And then multiplied by B1. So we said that don't worry about the negative sign because it's just the magnitude that you're plugging in here. 3.46 times 10 to the minus 5th. All then divided by the 4 pi times 10 to the minus 7th. And that's going to be equal to I1. Let's see what we get. So we're going to take that distance, multiply it then by 2 times pi, times then 3.46, good. And then divide that now by parenthesis 4 pi times 10 to the minus 7th. I'm using all exact values. I1 should be 10. We probably could have already made that prediction because if they're all 10, right, it's got to be 10 up there too to balance. So yeah, hopefully that kind of makes sense. And what's interesting is that, you know, it almost feels like, well, wait a minute, shouldn't these two have added like to 20 or something? Think about why that is the case, how that worked out. All right, and I just boxed in I1. I1 is equal to 10 amps, 10.0 amps, sig figs. Who knows? Guys, thanks for tuning in. Appreciate it. Please remember to help us out and subscribe, and I'll see you soon. All right, I'm getting a little loopy doing these problems. Take care.